Alright, in this problem we're looking at an automobile tire before and after a trip. It seems that the gauge pressure goes up as we take this trip, and that we have an initial temperature given. So we're pretty much asked to find out what's the final temperature of the air inside this tire. So we have this control surface of air. Obviously air is a gas, and we're told that we're told something about the initial pressure. So we're told that the gauge pressure is 190 kPa. Now the term gauge pressure means that it's the pressure that would be read off of, surprise surprise, a gauge. The only problem is that when we look at a tire gauge, for instance, just holding it in our hand when it's not connected to the tire, it doesn't read the atmospheric pressure. It reads 0. So in order for us to do this problem, we need to convert this gauge pressure into an absolute pressure. And the way we do that is we add on to it the atmospheric pressure here. So the pressure, the absolute pressure, the thermodynamic pressure at 1 is our given value of 190, and we have to add to it the atmospheric pressure, because this is the pressure that the gauge doesn't read on its own. It reads atmospheric pressure as 0, so we add on the atmospheric pressure to get the absolute pressure. In this case, we get 285 kilopascals. And then we're told that the initial temperature, which is also given, is 298 Kelvin. And we circle both of these, since we know that now at state 1 we really know everything. Given 2 independent intensive thermodynamic properties, the others are determined. Now we're going to go to a new state, state 2, and at this new state we have a new gauge pressure, P2, and it's equal to 215 kPa. We're going to add to it our 95, and that will put us at 310 kPa for this problem. Let's go ahead, or for this state. We aren't told anything about the temperature or the volume yet, so let's take a look at the problem. It seems that we have to know how we're going to get from 1 to 2 to really solve this problem, and that means we have to know what the process is going to be like. Well, in any tire that doesn't explode, the volume is pretty much going to become, or is going to remain, a constant throughout the process. So we're going to have an increase in pressure perhaps, and maybe an increase in temperature, but the volume isn't going to be able to increase very much without the tire exploding. So let's assume that the volume in this state is constant. So V is a constant. That would mean we're having isochoric transformation here, right? That's our assumption, and it's a pretty good one. That would mean that we could solve for our volume, V, at state 1, and that V2 would remain the same volume, V1, that we solved. So once again, we'd have 2 independent intensive thermodynamic properties, and from this we'd get our final temperature. So this is the strategy. It looks incredibly similar to what we've done before. We're ultimately looking for the temperature at 2. Our governing equation, once again, we can see we're going to need an equation of state connecting our state properties. For air, that's gas, so let's go ahead and use the ideal gas law again, as it is the easiest. Once again, R is determined by the type of substance. We'll find it to be 0.287 kilojoules per kilogram per Kelvin in a second when we look it up in the table. Let's evaluate this equation at state 1. So V1 is R T on P, all evaluated at 1, where everything here is known. And then at state 2, we ultimately want to know T2. which is going to be PV on R, all at 2. And we know that the volume has not changed, and the pressure at state 2 is given to us. So let's go ahead and create a new M file here. Call it tire.m. And start with our secret sauce again, and look up R for air. Here it is. Kilojoules per kilogram per Kelvin. And then put in our values of 190 plus 95 kPa, and T1 was 298 Kelvin. P2 is going to be 215 plus 95 kPa. And then we want to solve for our volume at 1, which is R times T1 on P1, meters cubed per kilogram. And we have T2, our desired temperature is going to be P2 times V2 over R. And we know that V2 is V1. So let's go ahead and just rename both of these volume, since there's not really two volumes to speak of in the first place. And let's run this very quickly, see what values we get. So we get our volume here is 0.3 meters cubed per kilogram, and our final temperature is 324.13 Kelvin, which is quite a bit higher. Let's make a plot real quick. We won't be able to plot it in the PV plane, or at least it won't be that interesting in the plane, because the volume is constant, and so that would look like a vertical line in the PV plane. Let's plot it in the PT plane. So let's let the pressure go between the initial and final pressures with 100 points in there, and then the temperatures are going to be equal to the pressure times the volume over the over R. So it would be equal to V on R times P. And you can see here that V is a constant and R is a constant, so this is really a slope, y equals mx, slope, rise over run of the specific volume over R. Let's go ahead and plot this then in the TP space. Our X label now is going to be in Kelvin, and our Y label will remain pressure kPAs. Alright, let's plot it. And you can see that it is indeed a straight line, as we would assume, or as we know from our analysis. And we can see that the temperature is linearly increasing with the pressure. So the air got very hot inside the tire.